Hello dear students, I hope you and your family are great. So in this video we'll solve 5 exercises on the central limit theorem, which is a very important topic of the module and for the exam. In particular, watch out for the recap on continuity correction in exercise 3 and the short computer simulation in exercise 5. Throughout the solution, we'll also use RStudio to evaluate PDFs, CDFs and quantiles, so that can be good practice. Please share your feedback, so for example, if you find these videos too slow or too fast, your feedback is very important for me to improve. If something is unclear, recall that you can always get in touch via email, or maybe you can just leave a comment below this video and I will reply. I'm organizing a TA session for the coming Wednesday at 2, but I'll keep you posted on that. Enjoy! Exercise number 1. Great, so let's read the exercise. Chris owns a laser pointer that is powered by 2 AAA batteries. A pair of batteries will power the pointer for an average of 5 hours use, with a standard deviation of 30 minutes. Okay, so we can start defining Xi, okay, as the life of a battery pack. And the distribution of these Xi's is unknown. Okay, however, we do know that the average life of a battery pack is mu, which is 5 hours. Let's write 5. And the variance of this life, it's equal to sigma squared, which is equal to 0.5 square. Okay, as 30 minutes is half of an hour, so 0.5 hours squared. Okay, so Chris decides to take advantage of a sale and buys 22 packs of 4A's batteries. So, well done, Chris. What is the probability that he will get to use his laser pointer for at least 105 hours before he needs to buy more batteries? Okay, great. So, basically Chris is about to use 20 battery packs, and we can define t, the random variable t, as the life, the total life, okay, of 20 battery packs. Of course, the life of these battery packs will be equal to the sum of the lives of each pack. Okay, and there's a total of 20 battery packs. Okay, we want to find the probability that t, the total life of 20 battery packs, so the total time Chris will be able to use his laser pointer, will be higher or equal to 105. So, as capital T, as the random variable t is defined as the sum of independent and identically distributed random variables, yeah, of course, and n is 20, so it could be large enough, we can use the central limit theorem. Okay, we'll use the first formulation that you've seen. So the probability for t to be higher or greater than 105, it's equal to the probability for t minus n times mu to be higher or equal than 105 minus n mu, which is equal, and we can divide both sides by the square root of n times the standard deviation. So the probability that t minus n mu divided by square root of n sigma square is greater or equal than 105 minus n mu over square root of n sigma 2. Okay, so this procedure is called standardization, right? We are carrying over the same operations on both sides of this inequality, so the inequality still holds. And now we use the central limit theorem. For the central limit theorem, we know that if t is the sum of n IID random variables with a certain average and a certain standard deviation variance. This particular transformation, okay, of t is approximately a normal 0, 1, a standard normal as n tends to infinity. So the probability we want to compute is approximately equal to the probability for a standard normal to be higher or equal than 105 minus mu n over square root of n sigma square. Okay, and if you carry over these calculations, this will be the probability for z to be higher or equal square root of 5. Okay, where z again is a normal 0, 1. Okay, then you can calculate this probability for z to be higher or equal than square root of 5 using the tables, or alternatively, much easier, much more precise and more straightforward, you can use RStudio. So I use the dark green to indicate that that an operation can be carried over with RStudio. So the command to do this is pnorm, right? So norm is the token for the normal distribution, and p represents the CDF of a normal distribution. We have to evaluate the CDF, but not the left tail, the right tail, but we will specify this later, of a normal distribution. So at square root of 5, sorry, in R, okay, we would use square root, so the function square is sqrt of 5, okay. We don't need to specify mean and standard deviation, as these are 0 and 1. When it's about our normal distribution, we don't have to specify these parameters, but we do have to specify that we are not after the lower tail, but the upper tail. So the command is lower tail equal false. And remember that this command is equal to writing 1 minus p norm square root of 5, so without the lower tail. So really this returns the CDF of a normal standard normal distribution, which is many times indicated by a phi. So this will be the phi evaluated at square root of 5. Okay, and so you have a script with all these calculations done in R, so please have a look at it, maybe try and compile the command so you make sure that everything is working and that everything makes sense, but the result is 0.01267 Okay. So the exercise is done, and this is the result. Of course, this is an approximation of the probability that t is greater or equal to 5, an approximation that becomes perfect as n tends to infinity. Just as a recap, the central limit theorem, okay, remember that the central limit theorem involves a sequence of xi IID, okay, the expected value, so they share a common expected value, which is mu, and the variance is sigma square. If you define t as the sum for I equal 1 to n of these xi, we can apply the central limit theorem, and there are many equivalent formulations of the central limit theorem. So I believe that the first one that you've seen is that t minus n times mu over square root of n sigma square is distributed according to a standard normal distribution. However, sometimes, like for example in the next exercise, maybe it's just more straightforward to see that t is distributed according to a normal distribution with mean n times mu and standard deviation n times sigma square. Some other times, instead of the distribution of t, we can look at the distribution of t over n, okay? This sometimes is well, this is the sample mean basically, right? Because t is the sum of all the random variables up to n divided by n, so maybe sometimes we can call this x bar, and x bar is distributed approximately, okay, according to a normal distribution. Well, we just have to divide the distribution at point 2 by n, so the mean will be just mu, okay, n times mu divided by n. However, when we divide a random variable by a constant, its variance is not divided by its constant itself, by the constant itself, but by the square of that constant. So the variance of these random variables is sigma square over n. Okay, and this is it. And this is a short recap about the central limit theorem. Exercise 2. Let's read the question. A certain financial theory posits that daily fluctuations in stock prices are independent random variables. Suppose that the daily price fluctuations in dollars of a certain value stock are independent and identically distributed random variables x1, x2, x3 with the expectation of xi equal to 0.01 and the variance of xi equal to 0.01. xi represents the increment in price of the stock on a certain day. Suppose that the daily price fluctuations in dollar of a certain growth stock, so we have a value stock and a growth stock, okay, but this growth stock, the increments, so the price fluctuations are independent and identically distributed random variables y1, y2, y3 with mean 0 and variance 0.25. So we can note down these numbers. We have the value stock, right, where the increment on a certain day has a certain distribution that we don't know, but the expectation is 0.01 and the variance, okay, is 0.01. Oh, what happened? Okay. For the growth stock, we have that, kind of a similar structure, so daily increments of yi, the average is, okay, the average of an increment is 0, and the standard deviation is much higher, so is 0.25. Right, let's go back to the question. Now, suppose that both stocks are currently selling for $50 per share, and you wish to invest $50 in one of these two stocks for a period of n equal 400 market days. So this is something that I'll note down. Assume that the costs of purchasing and selling a share of either stock are 0. Okay, no problem. So, well, the initial value of both stocks, so x0, let's say, is 50, which is equal to y0. But let's see if we'll need this. Part A. Approximate the probability that you will make a profit on your investment if you purchase a share of the value stock. Okay, so in order to make a profit, right? So I'm purchasing the value stock X for $50. In order to make a profit after 400 days, I will need the sum of all the increments in price from now in 400 days to be higher than 0. That way I can make a profit. So this part of the question asks us what is the probability of making a profit. So definitely we want to know the distribution probability of the sum of random variables to be greater than 0. Clearly we are dealing with a sum of random variables that are independent and identically distributed. We don't know the distribution, but we don't care. So we can use the central limit theorem and the second version that I've showed you in the short recap before. So we know that if we define x as this sum, okay, of random variables, we know that x is approximately a normal distribution with mean n times the mean of x, of xi, so 0.01, n is 400, and variance n times the variance of xi, so 0.01, and this is equal to a normal with mean 4 and variance 4, okay? So, of course, x is not distributed according to this, but this is approximate, okay? So, great, so we are interested in the probability for x to be higher than 0, which is approximately the probability for a normal distribution with parameters for 4 to be greater than 0. Okay, so easy. This probability can be computed with RStudio, so with RStudio, okay, and the command to do this is pnorm. So we want to evaluate this function at 0. So remember that pnorm refers to the CDF, so we have to specify that the mean is 4, and be careful, inside this function we always specify the standard deviation, okay, and not the variance. So we'll have to set standard deviation equal to lower tail equal false. Great. Again, I will recall that this is equivalent to writing P1 minus P norm of 0, 4, 2. Okay. Okay. So mean, you don't have to write mean equal for ST equal to, right? As long as you respect the order of these inputs. If you don't want to use RStudio, you can use the tables. For sure, for the coming test in 3 weeks, you'll be able to use RStudio, so my suggestion is to really be prepared to use RStudio to evaluate these probabilities. It's not difficult. However, with the tables, you don't have access to the tables for a normal with mean 4 and standard deviation 4. But with the tables, you'll need to standardize first. So if you want to compute the probability for x to be greater than 0, you will need to calculate the probability for x minus its mean, so 4, divided by its standard deviation 2, to be higher than, to be greater than 0 minus 4. So you standardize both sides of the this inequality, and this is a normal 0, 1, so you will have to calculate the probability for z to be higher than minus 2, and then you grab your tables and find this value. Equivalently here, for the standard normal distribution, you can still use the R function, and in this case you have P norm minus 2 lower tail equal false. Okay, so if you don't specify mean and standard deviation inside the pnorm function, RStudio will assume that the mean is 0 and that the standard deviation is 1. The result of this calculation, you can try and use R, it should be 0.997724999. Great. So, and this is the answer to this first to this first part. Let's move on. Approximate the probability that you will make a profit on your investment if you purchase a share of your growth stock. So this question is very similar to part A. So we make a profit if clearly the sum of all the increments in price of the growth stock this time are greater than 0, we use the central limit theorem again, right? And so we have that if we define y as the sum of all these random variables for I equal 1 to well, n, which is 400, then y approximately is a normal with mean 0, which is like the mean of yi 0 multiplied by 400, and standard deviation 400 multiplied by 0.25. That leads to 100. Okay, so we have calculated we have calculated the mean and variance of this function. However, to get the probability for y is equal to 0, we don't have to check any table, because this is a normal distribution centered at 0. The normal distribution is symmetric, and therefore this is exactly 0.5. So by symmetry, y. Symmetry. Great. So this is the answer to second part B. Part C. Let's read the question. Approximate the probability that you will make a profit of at least $20 if you purchase a share of the value stock. So this is a question very similar to question A, and in particular we are searching for the probability that x, our approximate gain for holding the value stock for 400 days, is greater than 20. Okay, this is equal, we can use straightforwardly RStudio, P norm. Okay, we want the probability for x to be greater than 20. Okay, we just state again that the mean is 4 and the standard deviation, okay, is 2. And don't forget lower tail equal false. Okay, and the output will be 6.2 times 10 to the power of minus 16. So this is basically 0. Right. For point number D, well, for the next part of the exercise D, the question is to approximate the probability that you will make a profit of at least $20 if you purchase a share of the growth stock. So same question, but for the growth stock. So the probability for y to be higher than 20, okay, same question, same formula, different numbers, so P norm. Okay, we are doing some practicing using these R functions. Mean equal, I don't have to repeat mean as long as I stick with the order, so it will be 0. And standard deviation will be, well, its variance is 100, so the standard deviation will be 10. Lower tail equal false. Okay. 0.02275. Last question, E. So assuming that the growth stock fluctuations and the value stock fluctuations are independent, approximate the probability that after 400 days, the price of the growth stock will exceed the price of the value stock. Okay, so I want to find the probability that the price of the growth stock will exceed the price of the value stock. This will happen if the total increments in price of the growth stock are greater than the sum of all the increments in price of the the value stock. Sorry. So this will be the probability that the sum from I equal 1 to 400 of yi is greater than the sum of all these xi. Okay. So do you think that this probability will be higher or lower than 50%? What do you think? Any idea? Okay, so you can't answer to me now, but think about it. I mean, it's kind of intuitive. However, to compute precisely this probability, this probability is equal to the probability of y, capital Y, that we've defined before, so the sum of all the increments of the growth stock to be greater than x, right? And this is the probability of y minus x to be greater than 0, right? We had the approximate distribution of y and we had the approximate distribution of x. Both were normal. So in question E, is stated that we can assume that these stock fluctuations are independent. So this normal will be independent, and W, defined as y minus x, is itself a normal, with mean, the difference in mean of the two normals, so 0 minus 4 minus 4. But the variance will be the variance of y minus x will be equal to the variance of y plus the variance of x, as x and y are independent by assumption. So this will be 4 plus 100. Great. Very similar to what we've done before, we calculate the probability that W is greater than 0, which is equal, okay, using RStudio, to the P norm 0, mean is 4, standard deviation is square root of 104, lower tail equal false. And the result for this calculation is 0.347443. Okay. Check the script that will contain all these steps in R.